I'd like to introduce Paul Dauncey, thank you very much, who will give us a talk about an update on what's been happening at the Large Hadron Collider over the last couple of years. Okay. Thank you.
Thank you very much. Okay, it's a pleasure to come and talk to you tonight. As Rod said, I actually work at the physics department here, so I'm used to lecturing. I'm not used to everybody being awake, though. So that's a good point for tonight. Okay, so I'm going to tell you about what's next for the LHC. So maybe I'll come around here. Do tell me we can adjust the lights if people can't see the slides very well. There's a couple of videos I know that are a bit dim, and I will dim them for that, but I'll keep them up otherwise. Okay, so I've tried to pitch this. I was aware there may be some people from schools here, but I know a lot of you have seen a lot of this stuff before. So I'll run through the standard model of particle physics. This thing's giving up. And the LHC accelerator and CMS experiment, but then get on to the bit that people maybe haven't seen so much before, which is what is new since the Higgs discovery. And then studies of physics outside of our standard model of particle physics. And then just one slide actually on the future of the LHC beyond that again. Okay. So particle physics is very basically, we're just trying to understand nature at its most fundamental level. So really what it comes down to is what are the elementary constituents of the universe and what are the forces that act between them. Okay. And so really we're looking at both matter and forces. And our answers for all of what we can see so far are 3 of the 4 forces are explicitly electromagnetic strong and weak forces, but notably not gravity. I will come back to that very briefly later. Are encapsulated in something called the standard model, which is model meaning it's a sort of technical term meaning theory to most people. So the standard model, the one that we all generally accept and does agree with all the data we have effectively, is what we're working towards, at least in particle physics. Now, the standard model itself was built up, pretty much started 100 years ago with relativity and quantum mechanics coming together. It took decades to understand how to really tie those two in. And then the obvious thing that had to happen as well was experimental data. So there's the theorists who are doing the theory, and then there's the so-called rude mechanicals, or the experimentalists like me, who build the experiments. So I'm not a theorist. I do the experiments. We put these things together and run them and analyze the data. Okay? The standard model came from both sides. Couldn't have been done without theorists, but it also couldn't have been done without experiments, because they told us which way to go. And so we end up with, as it says here, the sort of periodic table of the fundamental elements, which doesn't look anything like the chemistry one, of course. But this is what we think of, at least at the moment, as the most fundamental things. So there's 3 sets of, let's see if I can get this to work. No. Oh, there it is, but it's pretty weak. So 3 sets of families. If you look at the first column, U, D, E, and nu, E. So U, D are quarks, E is an electron. The quarks make protons and neutrons. The electron orbits around them. So atoms are made of the first 3 of those. Then there seem to be copies of them. The neutrinos are neutral, and they don't take part in atoms, but they're streaming through us all the time because they're created in the sun. Okay, so there's 3 families for quarks, 3 families of leptons, all of spin half. Then the forces, which are on the right-hand side, are made of spin 1 bosons. It's very important whether they're spin 0 or spin 1, for reasons that will become a little clearer later. And then right in the middle is the famous Higgs boson, which is spin 0. So it's different from every other thing in the standard model. So it looks a bit like matter, but it also looks a bit like force. And it has aspects of the 2. That's why it's interesting, because it's completely different from the other stuff we'd seen before. Now, in fact, the standard model itself, the theory, you can buy these mugs at Cern, which have the theory written out. That's in an extremely concise form, though. So you can't really do many calculations with this. If you actually want the full theory, you have to go to this. And wait. There is actually a minus sign error in this. If anyone can spot it, I'll give you 10 quid. Right, that is the so-called Lagrangian, the starting point of how you build the theory up. And you can see it's horrendously complicated because it's all the interactions between all those particles. There's many underlying symmetries there, otherwise it would be impossible to do, right? Which don't necessarily become apparent when it's written out like this, but those symmetries are used to write it in extremely concise form. That's really the point there. So the whole of the Standard Model has been built on these symmetries, and we therefore are looking for other symmetries as well, and symmetries will come up a few times in this talk. Okay. So, the history of the Standard Model particles. You can see I've outlined all of them except for the Higgs boson. So they date back from 1897 when the electron was discovered, and then a few more of the leptons down the bottom. Then in 1968 they made a big breakthrough at the top, realizing that protons and neutrons were not elementary particles but were made of quarks, and the UD and S were known then. Then there was the so-called November Revolution when they found the C quark up at the top, 1974. But even more critically, it turned out, 1975, we found the tau lepton. That was the first of the three families. That meant that there wasn't just 2 copies, but there was 3 copies. So, of course, then there was a big rush to try and find the corresponding ones. So 1977, 1995, they were found. And the final neutrino at the bottom row was actually only found in 2000. So there's pretty much 100 years between the first and the last there. On the right-hand side, of course, photons, people have been seeing photons since prehistory, so the discovery was cavemen or whatever. But then the gluon was discovered in 1979, and the W and Z in 1983. That was sort of the first discovery while I've been a physicist, really, which dates me a bit, but anyway. And then the final part, as I'm pretty sure everybody who's here knows, was 2012. So the one final bit, and in some sense the most interesting bit, the Standard Model, because it's different from all the others, was found 4 years ago, and there was obviously a big announcement at Cern for that. So you could say, we're done. We have got that, done the T-shirt. You will notice there is no Higgs on there. Whoever made that T-shirt didn't believe us, clearly. But the question is, have we discovered everything? We've got all the particles in the Standard Model. We've got this huge Lagrangian. So is that it? Clearly, that's not really the case. There are plenty of other things left to do. Lots and lots of big questions remain. So one of them is something so fundamental, people often forget about it. The origin of mass. Now, we think the Higgs is at least generating a lot of the mass in the universe, but we really still don't know why the electron has the value of 0.511 MeV for its mass, for example. It's that number, there is no universally accepted way of calculating that number that everybody believes in. All the other particles have different values. No one can explain that spectrum of those values. So something even as basic as that is outside the Standard Model. Okay? As you're probably aware, actually, the Standard Model, the matter, as we called it, is only 4%, 5% of the total universe. Okay? There's another 96%, of which something like 25% is dark matter, and then the rest is this stuff called dark energy. Dark matter seems like particles, so we think we have a chance of finding that as particle physicists. Dark energy, we leave to the cosmologists. No one's come up with a good way of seeing dark energy in the laboratory on Earth yet. Okay? We are looking for dark matter, though. Why is there no antimatter left? Right? There must be some slight imbalance between matter and antimatter, which means that we're all made of matter and there isn't antimatter elsewhere. That's a very good question. It's allowed in the Standard Model, but it seems to be 10,000 times too small to explain the amount of antimatter that we see. So that's a big open question. Neutrinos, they're part of the Standard Model, but they change into each other as they go. And as far as the Standard Model is concerned, that's not allowed. So there's something else new going on there as well. We can't go back beyond the first nanosecond of the universe at the moment, because that's the sort of physics that we understand. To push back further, we'd have to have higher and higher accelerators. Gravity, I mentioned. What the hell is gravity? Right? That doesn't fit in. No one's been able to come up with a fully consistent theory of gravity that's quantified using quantum mechanics, which can then be fitted into the Standard Model. And gravity comes into this thing of space-time dimensions. How many do we live in? Okay, I'll come back to some of these later. What it means is there's plenty to do. So for those of you who are thinking you're doing physics, don't think, oh, the LHC has ticked it all off. I won't bother doing that anymore. It's a great place to be. There's tons and tons of stuff to do. And this is going to take decades to sort out, if not centuries. So, you know, this is not the complete story. But let's see where we're going at the LHC. So, the LHC is an accelerator, Large Hadron Collider, based in Cern in Geneva. So why do we do these experiments, or rather, what do we need to do them, I guess is the point. So the accelerators, these are machines that make the particles go faster, as you'd expect from the word accelerator, and take them to extremely high energies so that you can bring them into collisions with other particles. We tend to send them around the ring in opposite directions and bang them together. You need something at the point where you bang them together, because they react, that can measure the particles coming out. And this is the CMS detector. This is the one Imperial's involved in that I'm a member of. Then you need some computing. Again, people often forget this. We generate enormous amounts of data out of these machines, petabytes. So that to distribute that around the world, allow people to analyze it, that's a major undertaking, and one of the significant expenses of doing these experiments, as it happens. And then you need an army of people to actually do the maintenance of the, well, build it in the first place, but do the maintenance, keep it running, and then analyze all the data. And this is a photo, if you can make it out. It's inside one of the buildings at Cern. The projection on to the side of the inside of the building is of the CMS detector again, and that is the members of the collaboration who happened to be there the day they wanted to take the photograph. The whole collaboration is about 3,000 people. So this represents about 1/3 of the whole collaboration. There was something like 1,000 people there. 3,000 people organizing that many people, particularly as, shall we say, academics aren't the most shy and retiring people. It tends to be herding cats is the expression that's often used. Trying to get everybody to pull in the same direction and have a common goal is difficult, but in the end, it's the physics that motivates everybody, and that's why we all do it. So it is a sociological problem as well as a physics problem at some level, getting all these people to work together. And there have been papers written about the sociology of these machines. So, okay, so we need particle accelerators. Why do we want to go to higher energies? What's the point in that? Okay, so one of the things high energy is equivalent to is temperature. So if you go to high energy, that's equivalent to having gone back effectively in time to when the universe was young and hot. And so that this is like a powerful telescope taking us back. We don't look with light, but we look back and see the conditions of the universe at a very early stage. We can also make new particles. E equals mc squared. If we have a lot of energy, it means we can make particles with higher mass, possibly that haven't been made before. New ones, which obviously now would have to be outside the standard model, because we've seen all the ones in the standard model. And then the other thing is, if you've got high energy, you can look in more detail at small objects. So specifically, de Broglie told us that if you have high momentum, which effectively is the same as energy at these sort of speeds, that you get a very small wavelength. And anyone who's used a microscope probably knows that the resolution is limited in a microscope by the wavelength of the photons, the wavelength of the light you use to look at it. So if you get a very high energies, you get very small wavelengths, therefore you can resolve things much better. And so we can see smaller and smaller distances. Okay? All these things are important for what we're trying to do. And to put this in context, what energy do the protons have? We would call it 6.5 TeV. That's tera as in trillion electron volts. Now, that's something like 4 trillion of those batteries put back to back, and you accelerate the proton in the electric field you get off that. Clearly, you don't use batteries. You use more like microwave ovens, in fact, that are distributed around the accelerator. But that gives you a sort of scale of how big these things are, right? Because to get to that sort of energy is extremely difficult, and that's why there's only one of these in the world. So I mentioned the universe. Here's the sort of history of the universe from, at the right-hand side, that's us.
The light down there.
Okay, fine, can do. Is that better? Yep. Right. Okay. So we're at the right-hand side, and as you go back in time towards the Big Bang over there, then now we have large structures, you, me, this lecture theatre. As you go back in time, because the temperature goes up, the universe is smaller and hotter, and as it expands, it cools down. So as you go back in time, it gets hotter. Then things like atoms can't exist anymore. The electrons get knocked off because things are moving around so much. So you have nuclei, and electrons. If you go back further, the nuclei themselves get broken apart, and so on and so on. The LHC, in fact, is probing this sort of region where even the protons and neutrons can't stay together, and it's a sea of quarks and gluons and electrons, WZs, all the particles in the standard model, just the raw particles not bound together. Okay? And that's the sort of conditions that we're trying to study, and the further back we can go, the higher the energy. Sorry, the higher the energy, the further back we can go, and therefore get closer to the origins of the universe and study the conditions there. So that's the idea. Now, the actual LHC is shown here. This is obviously an aerial photograph. The thing on the right is Geneva Airport. So this is 27 kilometers around. It's the same size as the Circle Line, but the particles go around a hell of a lot faster than people do on the Circle Line. So, and you can see that there's a smaller ring inside, which was actually frontier physics in the 70s and 70s to 90s, really. And then this ring was first used for colliding electrons and anti-electrons, positrons, and now it's used for colliding protons and protons. Okay? Now, it all starts from a bottle of hydrogen, which is where the protons come from. Literally, there is a bottle of hydrogen that they connect on, which then, I hope this will work, yes. So you take those out, you ionize them, basically. LINAC means linear accelerator. They get put in a booster, which just gives them an extra kick, but then they're stored in the ring there, which is the old proton synchrotron. That was frontier physics in the 50s. That then injects them. Now they go underground. That's because the radiation levels are so high. So you need to work these experiments underground. It also shields you from cosmic rays that can cause your detectors not to see as well as they would otherwise. It goes into the superproton synchrotron and then into the large ring, which is the LHC itself. And there are 4 experiments on there. So 2 general purpose ones, Atlas and CMS. And as I said, we're involved in CMS. And then 2 more specific ones looking at particular aspects, which are LHCb, looking at B mesons, and ALICE, looking when the LHC can also collide nuclei together at lower energies than they do with the protons. But they're interested in large nuclei collisions. And so their detector is dedicated to that sort of thing. So CMS here, on the opposite side of the ring from Atlas, is the one we work on. It's buried 140 meters underground, close to the Jura. If anyone's been in Geneva, the big string of mountains you can see in the background. So there, it sort of looks pretty small. In reality, it's actually pretty big. So this has, you can see there's 5 chunks. The one in the middle has this solenoid or magnet, a big solenoid magnet. If you've ever had an MRI scan, that's a superconducting magnet that they insert you into. So this is effectively a similar concept, but this one is much, much bigger. I'll show you a photograph of it in a second. I won't go through the various parts here. Each of these sections measures something particular about the particles. Okay? The usual way it's described is a cylindrical onion, that the particles, as they travel out, they're actually created in the center of CMS, and so go shooting out in all directions, and so they pass through all this material, and that's how we tend to measure them. Okay? To put the scale on here, you probably can't see until I circle it. That's a human. This detector is bigger than this building. Okay? And it's fully instrumented inside down to the sort of 100, 200 micron level, really at the center, for example, in terms of very high-tech electronics or pieces of equipment that can measure charged particles or neutral particles, whatever types of particles they're after, as they zoom through. Okay? So this is a sort of engineering feat to even put this thing together. Now, as you can imagine, this sort of thing is very expensive. If you're budget limited, you can buy the Lego version, but we, of course, have to use the real thing, and this will give you an idea of what it is. This is just the middle section with that solenoid, as I said, a bit like the one that you'd have for an MRI scan. You can see the size of the people relative to this. This must be 8 or 9 years ago, when they lowered this thing down from the surface, down the 140-meter tunnel tube, to get to the bottom where it will actually run, and has been running since 2009. So it flips now to the lower thing down in the cavern as this thing comes in. It took the best part of a day to do this. Clearly, you have to move something this heavy very carefully indeed, and hence the time-lapse photography. But that was one piece, the middle piece, of the whole of the CMS detector, so you can get an idea of the scale there. So the CMS detector, again, this is the end-on view. Just some numbers, as I said, there's about 3,000 scientists involved from 40 countries, now 170 institutes. And I think we've hit the mark of 1,000 PhD students just last year. So this is a major industry, if you like, for particle physics, to churn this number of people through and do all the work and keep them the coordinators, as I was saying. So the important bits of this, basically the detector divides into 4 pieces, which is sort of useful to know. So the innermost bit is the so-called silicon tracker. Flat pieces of silicon, each one's about the size of my hand. As a particle goes through, it causes ionization in the silicon. The electrons that are ionized can be detected as electrical charge. So you have some very sensitive amplifiers on there that can detect that charge, so it tells you where it goes, to 10 or 20 microns, right? So it's very accurate. That's the central piece. Next out is a calorimeter, so-called electromagnetic calorimeter, scintillating crystals. You can see one of the crystals in the foreground of the photograph. When a particle goes into there, it causes scintillation light. You can detect the light with a photodetector. Sort of a bit like a camera mounted on the back. From the amount of light, you tell how much energy the particle had. Further out again is brass interspersed with plastics insulator. The brass causes the particles to splatter out. They hit a nucleus, all sorts of stuff showers out the back. This insulator then sees all those particles going through again by producing light. And the final part, which is actually the biggest, thickest bit, it's all the red part that takes up most of the detector volume, are very simple chambers because they had to be as cheap as we could make them to fill up so much of an area. They're basically flat planes filled with gas. A particle goes through, causes ionization. Then in the gas, the electrons, they don't go back onto atoms. You can actually get them to drift if you put an electric field across, and they'll be collected. So you can tell a particle went through. Okay, so those are the four major bits. So how this all fits together, I might even have to turn the lights down again. I'll bring them back up again in a second. No. Try that one. Okay, I hope this is visible. So this is a video of the CMOS detector we're going in. This is the tracker. You can see many, many lanes of silicon. The particles collide, they go out. Those are measured by the tracker. The blobs outside are measured by the calorimeters. And so the whole thing is reconstructed from the data that we see. This is without the detector in the way. So it gives you an idea of what these events look like. A stream of tracks, particles, charged particles coming out from the inside. Okay. So this is a sort of cross-section through just one little wedge of the whole thing. It's obviously circular. You can see the small thing at the side. So all the particles with charge, as I said, leave tracks in the silicon tracker. So you can see charged particles went through. Then the green part, which is the first of the calorimeters, electrons and photons are the only things light enough to actually deposit all their energy in there. Everything else punches through it. It's not that thick. So any splodges there, you can tell are electrons or photons. Anything that makes it through there normally interacts in the yellow part. Much thicker, deeper calorimeter that measures the energies of hadrons, protons, pions, kaons, effectively. The one type of particle that lives long enough to actually get out from where the collision happens and get all the way through is the blue line, which is a muon. So you can tell muons very easily. They're the ones that get through everything. And that's the chambers at the outside, the big, cheap chambers. Those are the ones that are used to detect muons. So that sort of tells you how to interpret the events. So as an example, here we have a Z boson, which was discovered back in 1983, decaying to two muons. You can tell they're muons because they do have hits. If you project the tracks through, you can see that the muon chambers have lit up. They've got things in them. So what can we do with this? How do we, even though it's a Z, all we see are the two muons? Well, the first thing is, Einstein tells us E equals mc squared, clearly. What that means is, if we measure the energies and momenta of the two muons, and you use the right equation, you can add them up to find the overall energy and momentum, and therefore the mass, using Einstein's equation, of the thing that created them. Because the mass must be conserved, right? It's the same amount of energy and momentum must be the same amount of mass. And so by adding those up, you can check, yes, this did come from a Z boson because it has the mass of the Z boson. Okay? So we produce copious amounts of muon pairs. And this was done within the first few weeks, this plot. But it's so famous, people keep showing it, and I'll show it again. This shows, if you just take all the muon pairs and combine them together, there's an awful lot of just mismatched pairs that don't add up to any particular mass, but each of the spikes is a physical particle that's being created and decaying to two muons. So the ones up at the top right, top left, excuse me, those were all discovered back in the sort of 50s and 60s. Then the ones, the J size, the ones in the middle and the upsilon, those are discovered in the 70s, and then the Z was discovered in the 90s. So in some sense, this is a sort of history of particle physics plot as well. Although it was all created by CMS, it shows particles that were discovered over the previous decades. But a particle, the point is, a particle shows up as a bump. That's the critical thing, because you can combine them and find out what the mass of the thing that decayed was. And if you get that right, then it'll agree within sub-experimental resolution. Okay? So how did we use that to actually find the Higgs, just to bring us up to where we've got to? The Higgs decays in several different ways, as I'll show later. And on the left, it decayed into two photons. The two big green spikes are amounts of energy deposited in the first calorimeter. So we know they're photons because they're in that one. And again, you can add up their energies, the momenta, and find out what the mass was. In the second one, it decayed to two Zs. The Zs themselves then decay. In all cases, the Higgs and the Zs never make it out into the detector. They don't live long enough to get that far. So we only see their decay products. The one on the right, The two red splodges down the bottom, it's a different color thing from the other ones, are, again, electrons. They're in the electromagnetic calorimeter, so you can tell which one if there's a track on them. And then the green splodges up at the top show two muons. It's a bit hard to see because the light isn't very good here. So basically, that's one Z going to two muons, the other one going to two electrons. But these are the two channels, and this is how we see these events. So when people say, how did you find the Higgs? You don't sort of look under a stone and find it there. You see things like this. So explicitly, the Higgs goes to two Zs, to four leptons, so either electrons or muons. This is, I think it's quite a good way of seeing, we got a bunch of data over 2 years, just before we made the announcement, and actually a bit afterwards in this plot. So it builds up, and you can see the data is wrapping up at the top. So that's where we got to by the end of 2012. Now, partway through, seeing that peak of the red peak, which is the Z, the one to the left is one Z, the one to the right is two Zs. So the one in the middle is the Higgs, the red one. Seeing that when you'd only got a small amount of this data just wasn't possible statistically. It just looked like the fluctuations. So that's the trick. You've got to have enough data to be able to say there's definitely something there. And this shows the sort of status of where we were at the end of 2014. So on the left is the plot of masses, and we're looking for a mass peak, just like I showed for the Zs. And here there's an enormous amount of background. So you've actually got quite a small peak on a very large background. The bottom plot shows it with the background subtracted, the smooth curve, if you like. And you can see there is clearly a peak there. The right one is the one I just showed for the other one. It quotes this 5.6 sigma and 6.5 sigma, basically, which is the statistical importance of this, if you like. But to put that in context, as it says across the bottom, 5 sigma means 3 million to 1. And to be absolutely clear, what that means is, if there was no Higgs there, the chance of getting a peak like the one on the left of that size, even though there's not really a particle there, it was just a statistical fluctuation, is 3 million to 1, which, for my betting, is perfectly good enough to say, yes, it really exists. But of course, you have to say it really exists at the 5.6 sigma level if you're being proper as a scientist. Okay, but everybody believes there is a Higgs there. Even the Nobel Prize committee believed there was a Higgs there, and so Peter Higgs himself and Francois Rongley were given the Nobel Prize the year after the discovery for that. Okay, so that sort of brings us up to, the Higgs discovery itself. Sorry, I'll just take a drink. So the question is, what's happened since then, and what are we doing now? So, what's new since 2012? The big thing, the big deal that's changed since 2012 is there was a shutdown in 2013-14 where the accelerator was upgraded so it could run at higher energy. Specifically, we went from 18 to 13 TeV, so that's 4 TeV for each of the protons, giving us 8 in total to 6.5 now. Now, that doesn't sound like a big deal, 8 to 13. It's only sort of like 50% more. But you've got to understand how these reactions happen and then see why that is a big deal. Top left, the protons, you learn that a proton is made of a U, and a D quark. Okay, as an undergraduate. It's not really true. There's a mess of all these so-called virtual particles that are created and disappear again. They get absorbed back or get exchanged between them. Gluons and other quarks there. So the proton is a whole bunch of other particles. And when they're moving, all those particles are moving along as well. Now, of course, momentum's conserved. So the total proton momentum is shared between all those particles. And there's hundreds of them or thousands of them. It depends, in fact, on how deeply you probe into the proton as to how many there are. The plot on the right is supposed to show you a rough idea of what the spectrum is of the fraction of that proton momentum that's carried by these things. And you can see that it goes from 0 to 1. Very, very rarely does one of those constituent particles inside one of the quarks or gluons actually have something like the proton momentum. Usually it's at most 10%, and in fact it's even smaller than that a lot of the time. So when you collide two protons, you collide the internal constituents, but you only get 10% of the energy from this one, 10% of the energy from that one. So the overall interaction can be actually much, much smaller than your 8 or 13 TeV. That's a problem. Obviously, we'd like to get as much energy as possible. But what happens is you've got these exponentially falling things, and if you think effectively what you're looking at is the overlap. If you want to make a new particle, you've got to have both of them high energy. If you up the energy a bit, that overlap becomes much, much bigger. So in fact, even a 50% increase in the energy, the plot at the bottom, the scale is 1, 10, 100. If you're looking in the 1000 GeV, so that's a TeV, a trillion electron volts, or higher, then the increase, this is the ratio of the rate at which you get those sort of collisions before and after the upgrade, goes up by a factor of 10 to 100. Okay? So what this says is just that small factor in the energy means that we're 10 or 100 times, depending on the mass of the particle, more likely to see new particles now than we were before. So a month's running now is effectively equivalent to a year or two's running previously, which means we're in a completely new regime. We've got sensitivity to potentially see particles that we could never see before. And so this is really the focus. So TeV is really where we're interested in. Those are the sorts of particles that we're looking for. So that's the number to remember. Now, of course, we've finished the standard model. So now the whole name of the game is to find things that don't agree with the standard model. Anything we find that doesn't agree with the standard model is going to be a big deal, potentially a Nobel Prize for whoever discovers it. Okay, but of course, we need to know where to look. And now there's no guidance. We knew where to look for the Higgs. We knew how it would be created, how it would decay. It was easy in some sense. So it does feel a bit like this, right? You know, we don't know where to go. Now, luckily, of course, as I said, I'm an experimentalist. We have our theoretical friends who help us. But it's a bit like that as well. They're shouting at us saying, no, 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 my theory is right. No, mine is, mine is. And it's sometimes very hard to really understand what are we supposed to be looking at and what is the most likely thing that will show up something beyond the standard model. Okay? So I've divided it into two parts. There's what I'm calling here the known unknowns, and the unknown unknowns are later. So the known unknowns are basically saying, we know the standard model, we're looking for things beyond the standard model, let's use the standard model particles, which we can create and we know are there, and measure them as precisely as possible to see if some of them are actually not really acting like they should be acting. Okay? And in particular, the one that we're doing here, we're looking at the Higgs. And that's because the Higgs really does look different from all the others. It has all these weird properties, and therefore we thought this is the best bet. Right? So we listen to the shouting of the theorists and have to make our own minds up where we're going to put our time and effort. So we at Imperial are looking at doing precision measurements at the Higgs, or at least developing in that direction. So we need to know a little bit about the Higgs to understand why we're doing this. Okay? So basically, the Higgs is there because we want the electron or any of the other particles in the standard model to be able to have a mass. Turns out the fundamental theory says they should all be massless. And as I'm pretty sure everybody here would know, if something is massless, it has to go at the speed of light, like the photon. Okay? So everything should be moving at the speed of light. Now, blatantly, I'm not. So therefore, this can't be in agreement with experiment. And that's where the Higgs comes in. So the basic idea was that there is something, the particles are really, inverted commas, massless, and therefore should really be moving at the speed of light. But there's a pervading field, in the technical term, but effectively it gives friction to everything. Right? It's there all the time in the whole universe. As things move around, they feel the friction of this field being all around them all the time. It slows them down. Now, different particles have a sort of different friction coefficient with this, if you like. It's the same field everywhere, but different particles rub against it harder or softer. And that appears to us like a bigger or smaller mass, because if it rubs a lot, then it's slowed down a lot. It seems like it's got a big mass, and hence is going much slower than the speed of light. Now, the other subtlety is there's the field and there's the boson. Right? So this is the Higgs field. Now, quantum fields are basically you have the field, and then if you excite it up to another level, you can't just have an arbitrary amplitude on the field. It has to go to particular values, because it's a quantized system. And so if you knock it up to the first energy level, that corresponds to there being a physical particle. If you knock it up to the second one, there's two physical particles, and so on. Okay? Now, the quantum, the first quantum, is the Higgs boson that we've seen. So we haven't actually observed the field, except for the fact that we hypothesize that's what gives everything mass. What we've seen is the excitation of the field that gives us the boson. Right? But it's the properties of the field which are more fundamental, if you like. And so we want to try and understand the field. Now, we think it exists because we've seen the Higgs boson, but we want to dig into this more. The point, the really interesting thing about this field is it's very weird, right? That if you have a vacuum, there's no electrons in it. The electron field is exactly equivalent in some sense, is effectively zero there, right, on average at least. It fluctuates around, but it'll be zero. The thing about the Higgs field, if it was zero everywhere, there'd be nothing to have friction against. So you've got to have a field that is actually has a value even in a vacuum. And that's the really hard bit, and that's why it took a long time before people figured out how to do this, Higgs and Englert in particular. So the point is the field must have an amplitude even in the vacuum, in empty space. And the jargon is the vacuum expectation value. Expectation value is a fancy word for saying average. So its average value in the vacuum cannot be zero. How on earth do you get that? Right, so the point is it's allowed by the so-called potential, which you can think of just like a potential in normal classical mechanics. So a normal field like the electron has a potential shape like this. It's quadratic, so phi squared. Phi is the field value. But you can think of this just as a sort of dip in the ground, if you like, and you're rolling a football into it. Okay? Clearly, the football will want to be at the bottom of this dip. And so that's where it will want to sit. And so at that point, relative to the point at the bottom, it has zero distance from there, right? So the field amplitude is zero, the equivalent of. Now, the Higgs field has an extra term. It has a phi to the fourth term, and in fact has a negative phi squared term, which means it has this weird shape. And now it's symmetric, backwards and forwards, just to be clear. Fundamentally, both of these are left-right symmetric, okay? So there's no difference from that point of view. But clearly, the one on the right, that's not a stable situation, right? You've got this ball precariously balanced at the top of the peak, and any little vibration, anything, it will make it roll down one side or the other. So let's assume it just happens to roll to the right, okay? What you've done here is you've now broken the symmetry. There's nothing really not symmetric about this situation, but the eventual solution you've ended up in is not left-right symmetric anymore. This means that the field, this is tightly coupled into the fact that the field now is not at the center and therefore not at zero. And so this is what's happening. So this term spontaneous symmetry breaking happens like this. It's effectively one, there's a lot of analogies for this. One is just, you can try and balance a pen or a pencil on its point. If I take my finger away, which I will in a second, clearly it's not going to stay there very long. It falls that way. It could have fallen in any direction. It chose one just because of a little bit of breeze that probably blew it, right? But it has to go one way or the other. It can't be a symmetric state. And so this breaking of the symmetry is completely tied in with the fact you can then get the field to have a non-zero value in the vacuum because it goes to the lowest point. And that is the vacuum, effectively. And that allows us then to have the friction. In fact, the field is two-dimensional. It's actually a complex number, so Argand plane. So this is actually not just left-right, it's rotationally the same all the way around. And it's often described as a wine bottle potential. There is a literal wine bottle that's been sawn off, so you can see the inside of it and see why it's called a wine bottle. Do not try this at the drinks afterwards. It makes a hell of a mess, right? Just to warn you. So, yeah, so it's the wine bottle potential, and it's the same principle. It wants to sit away from the center. And now you've broken the symmetry, you've got a value that's not at zero, and that allows the whole friction thing to happen. And then small oscillations around that, as I said before, those are the quanta that then give you real fields. So that the field is given by the vacuum expectation value, and then the Higgs itself, the actual boson, that is the oscillations and the bit of the field that still moves. Okay, so, as I said, we've discovered the Higgs, so now we want to try and measure it as carefully as possible to see if it really is as the standard model predicts. I've said a few times it's very different. It has no intrinsic spin, unlike every other particle in the standard model, which are continuously spinning on an axis, at least in a classical picture. It acts a bit like a matter particle and a force particle. Nothing else does that, right? And it has this unusual potential shape. None of the other particles have that. This one is really unusual, and it would be very easy for it to actually not be what we think it is. And that's why we're putting our bet that this is the one we should look at. But what can we actually do in practice, right? We don't ever see these things. They decay in the middle of our detector to other particles. So what can we test? Well, the things that we actually have experimental ability to do is we can see how often it's produced, okay? The so-called cross-section, because it's the size of something that the proton would have to hit to make it happen. So it's like a little target. That's how you quantify it. How often does it decay? I said it goes to 2 photons or 2 Zs. That's not the only things it decays to. The standard model predicts exactly how often it should go to those things, so we can go and measure those. One interesting thing is, does it feel its own friction? Right? The Higgs will feel itself as it moves around as well. And so that leads to an effect which would be very interesting to see, but probably we won't see for a long time. But there's even more of a basic. Is there only one? There's nothing in the theory that says there has to be one. It's just the most economical. Occam's razor says take the simplest thing. Could be more than one. Of course, that leads in, anyone who keeps an eye on what's going on at Cern, to the so-called 750 bump. Okay? So we took data after this new upgrade to the higher energy. We took data in 2015. And by the summer, Atlas, which is the other detector that we don't work on at Imperial, but is a similar level of detector, and CMS, the two side by side, you can see around 750, there seemed to be the development of a little bump. Now, this is not 5 sigma, 3 million to 1. This is more like 2 or 3 sigma, which is sort of 1%, 1 in 100, not 1 in 3 million. So everybody had to retain a little bit of skepticism, but basically people started getting really excited because this would have been the first ever particle discovered outside of the standard model. So, but of course, we had to wait, we had to build up more data before we could really decide. The theorists, nearly 1,000 papers came out from this, generated within a few months. I mean, it was amazing how fast people came out with new ideas as to what this thing could be. Of course, as I said, there could be a Nobel Prize in it if you got it right. So there was a lot of interest in this thing, of course. Now, unfortunately, we went to 2016. 4 times as much data, so we can neglect the bit before. Of course, it's all added into these plots, and you can see there is nothing there. This is statistics for you. It's really annoying when it happens, but that's the way it works sometimes. Little bumps disappear as you get more data. That's why it's always good to have more and more data, because you can overcome the statistical fluctuations. So this one, annoyingly, turned out not to be anything real, unlike the first one. You can't win them all, right? But let's go back and see. So we've got to go back to the measuring the standard model more accurately rather than finding bumps and making massive discoveries straight away. Detailed plot, basically what it's saying is there's 4 different ways you can make the Higgs. This one up here dominates, and in that case, if you look at these diagrams, the Higgs is coming out on the right, there's only the Higgs there. So you just make the Higgs particle and nothing else. The next one down, you make a couple of quarks. The one over here, you make a W or a Z. And then this final one here, you make a pair of tops. I've done it in that order. Basically, the quarks are lighter than the W's and Z's, and they're lighter than the tops. So it's easier to make them, given that you're always energy limited due to the way the proton collisions work. So the top one is the most common one, because it's just the Higgs, then the next one, then that one, and then that one. And so you can see that they come down in that order in the plot, which tells you what the cross-sections would be in the standard model. So one of the things we're going to try and do is measure those 4 separately, and you can tell which one it is by what's coming off along with the Higgs. And so we try and measure those and see if they're in agreement. As I said, the other thing about it is its decays. Now here's the plot of the decays. The vertical line is pretty close to where we actually measure the Higgs mass. Now you can see in some sense we got really lucky. If it had been at 170, for example, it would have been 100% to W's. All you could measure is Higgs to W's, and you wouldn't see anything else. You'd have no way of checking the standard model. Whereas here, we've got a whole bunch of different ways it can decay. So if we can go and measure as many of those as we can check that they really are gamma-gamma, 0.2%, for example, the ZZ, 1.6%. We can try and measure those things and really see if they agree with the standard model. This is what I mean by making precision measurements to see if it's really there or not. So production and decay, both actually summarized in this plot. Now, the top left actually gives you the punchline straight away. The overall rate, compared to the standard model that we see, is 1.09 plus or minus 0.11, which means basically 1, very consistent with. Okay? So the bottom line is, even with the newest data from the LHC, it still looks exactly as we would expect for a standard model Higgs boson, which is the boring answer, but in some ways it's still interesting. But we're going to keep digging, of course. The first half of the plot is the cross-sections, the separate ways of producing it relative to the main one, because we can measure the main one quite accurately, because it's the most common one, and then we measure the others relative to that. Now you'll see all the error bars are very large. They're all consistent with being 1, as in relative to the standard model rate, but the error bars are huge. So there could be discrepancies in there that are hiding that we just haven't got enough data yet to find. Similarly, the bottom half is the branching ratio. So these are all relative to the branching ratio for Zs, but W's, gammas, taus, and B's. So, it goes apart to the different ones. Again, all relative to the value you get from the standard model. They're all consistent with 1, but in particular, the B's do look low. So people are taking a particular interest there. It's a very hard measurement to do because the B's just look like quarks and just give a lot of hadrons. It's very hard to identify the B's. But at the moment, everything is statistically consistent, and sometimes statistics goes away, sometimes it turns out to be something interesting. So that's one to keep an eye on. Now, this is production and decay separated, but the actual amount of the friction that the Higgs has with each particle, which is its interaction, affects both the production and the decay because it comes in on both sides. So one very nice way to plot this is to plot it as a function of the interaction to each of the particles. Now, the whole point is that interaction gives the particles mass. That's what it's for. So if everything is working right, then the mass of the particle, which is shown on the x-axis, should be directly proportional to the measured strength of the interaction on the y-axis, which we measure from how often it decays or how often it's produced. And you can see that there is an extremely good agreement across there. The B's are a little low, reflecting what we've seen in the other plot, but they're still statistically okay. The error bar goes into the region that the line is. So at the moment, it really, really does look like the Higgs. And these particle masses vary by 3 orders of magnitude, and so do the interaction rates. The friction coefficients, if you like, vary by a factor of 1,000, but are very well in agreement with the masses. So this thing that we have measured really does look like the Higgs boson from the standard model. It doesn't look like a bump that turned out to be something completely different, okay? But the error bars are still huge. In fact, we've only really measured one of those 4 production modes with anything like a statistical significance. So there's a huge amount that we could do if we had more data. Right. The Higgs self-coupling. This is one of the untested parts, this weird shape. Basically, I said there's a quartic term, v plus h to the 4th. That will end up with v3 and v4 terms. I'm pretty sure everyone knows how to expand out a bracket to the 4th. So basically, what this says is this was the dominant production mode before, but if you've got a h to the cube, it means you can have diagrams like this, 3 Higgses all touching each other, which means instead of producing 1, we'll actually see 2 occasionally. So we would have 2 Higgses being produced at the same time. Now, unfortunately, the standard model says this is a very, very low rate. Okay? So we probably would have to run for 20 years to see it. But of course, if it's not the standard model, it could pop up next year, or 2 years from now, or 6 months from now. So, we're looking, for example, 2 Higgs. One of them goes to B's because that's the highest rate. One of them goes to gammas because they're very easy to identify. We haven't seen any sign of this yet. We don't expect to see any if the standard model is true, but of course, we're looking for breaks in the standard model. Now, it's not just the Higgs. We're looking at CMS-wide, although we at Imperial are concentrating on the Higgs. We're looking at W's and Z's, tops, and Higgs, which are the sort of main things that haven't been studied as much before, because they're the main things that you can produce at the LHC compared to the previous ones. Here, the gray bars are the standard model theory predictions. The data points are the blue and red colors and green colors, and basically everything is in agreement so far. It's all consistent, which is very boring at some level, but it does tell us how fantastic the standard model is. That's the other thing. The Higgs to 2 Higgs, by the way, it's off the bottom of this chart. We need a lot more data before we're going to see that, as I said. It's just such a low rate. The things here vary, top left, excuse me, just single W or Z, you get about 100 a second, down to these very obscure Z and a photon and 2 jets type things, which are 2 a month. Right? So there's 8 orders of magnitude difference, and the standard model agrees over this 8 orders of magnitude. So it's quite amazing. But the overall conclusion is, for the known unknowns, things from the standard model, we don't see any discrepancies. All right? So the latest data are still in agreement. So the final chunk of the talk. I said the known unknowns, these are the unknown unknowns. These are the sort of more exotic stuff. We do actually have a study group inside CMS that is called the Exotica group. Right. Yes, I do wonder how many of their emails get eaten by the spam filters. But anyway. So they are looking, again, we have a group from Imperial. I personally working on the Higgs, but my colleagues are working in this area, looking at things like supersymmetry, dark matter, extra dimensions, all the sort of stuff that you hear about in the Scientific American. And we're actually trying to see if that really exists or not. So that's the point of this little bit. So supersymmetry, right? Supersymmetry sounds fantastic when it was first invented or discovered, depending on your philosophy of mathematics, if you like. in terms of the mathematical theory, it seemed really, really interesting, and it still does. But everybody thought this must be true. Before the LHC, you would hear theorists saying, oh, when we discover SUSY, not if we discover SUSY. So supersymmetry. Basically, Einstein's theory of special relativity is based on a symmetry which nowadays is called the Poincaré symmetry, right? Which is the symmetry, basically it boils down to the speed of light is the same no matter how fast you're moving. Okay, now, there is only one possible extension, as far as we know, for that, and that is this supersymmetry theory, which basically boils down to saying all of the bosons, the ones who spin 0 or 1 in the Standard Model, and all of the fermions, which are spin 1/2, have a partner which is the other type. So the electron, which is spin 1/2, has a partner which is the SUSY electron or selectron, which is spin 1 in that case. Okay? It could be spin 0 or spin 1. I think it's spin 1 in most of the theories. Now, what this says is what we consider as matter of one type and force of a completely different type are actually completely intermingled. And so it would completely change our view of how the universe works if this was actually true. Okay? There are several other interesting consequences. The SUSY-ness, can't think of a better word for it, the quality of being a SUSY particle as opposed to a normal particle, so the ones on the right as opposed to the ones on the left, it's like a charge. Symmetries produce things like charge. Electric charge comes from a symmetry. And so this supersymmetry produces this charge. What that means is one of the particles over on the right-hand side has that charge. It's the lightest one. There is nothing it can decay to, because it can only decay to lighter things, which are standard model particles, nothing to decay to without that charge being disappeared somehow. And you can't force the charge to go away. It's conserved, which means one of the particles on the right has to be stable. Okay? If it was normal charge, we'd have seen it. They're streaming through us all the time if this theory is correct. So a neutral particle over there must be stable. There is one that will always exist. It's called the lightest supersymmetric particle. This is a critical point. Okay? SUSY also has, if you look, there's 4 extra Higgs bosons besides the one in the Standard Model, but unfortunately not at 750 GeV. This was one of the reasons why everyone got so excited. It looked like it could be the final confirmation that SUSY actually exists. Turned out not to be the case. And it also helps explain the mass of the discovered Higgs. Now, I haven't said why we have to explain it, so I'll just go into that very briefly. Basically, the Higgs itself, it causes friction on the particles. It's like force, action, and reaction. That means that the particles put friction onto the Higgs. They actually make it more massive because they cling to it. It's like when I have 2 teenagers now, but when they were younger, they'd cling onto my legs. Trying to move around with 2 children on is very difficult. So it changes the mass of the Higgs itself because of these particles clinging to it. Okay, so the different particles cling in different ways, but they do give it a different mass. So you can think of it as the bare mass, which is the one it would have if we could turn off the interactions. Then all these particles clinging to it gives it a different mass. Okay? Basically, the Higgs mass squared is equal to the bare mass squared minus some correction, which is due to the calculation of all these things clinging onto it. Now, no one knows how to predict mass. Right? That was what I said at the beginning. Mass is one of these uncertain things. We just plug in numbers in the Standard Model. We don't know why the masses have their values. Now, any theory beyond the Standard Model, we assume is something like a grand unified theory, which is going to be 10 to the 15 GeV compared to the 10 to the 3 GeV that we're looking at now. Huge scales, sort of universe-type scales rather than the sorts of things we can do. And that means the 2 terms that have to cancel out, because they're squares, they're 30 order of magnitude, 10 to the 30 minus 10 to the 30 to give you 10 to the 2. So that little constant c would have to be specified to 28 significant figures, right? People just say that's completely crazy. A constant of nature just has to be that fine-tuned to give us what we need. Sounds like it can't possibly be true. They say it's sort of aesthetically ugly, and nature wouldn't like aesthetically ugly things. It wouldn't allow them to exist. Living proof that's not true. Different problem. But anyway, the point is, all these particles, it turns out that the fermions push it one way, and the bosons push it the other way. And the whole point about SUSY is it has an equal number of the 2, because each one has a mirror particle. And so what that means is one gives you a plus, one gives you a minus, and they will cancel out. Okay? So this huge number of corrections, which would normally be thought to be 10 to the 15 GeV, are effectively 0. So then there's no problem at all. The Higgs mass can be what it is. There's no fine cancellation. So it looks much more natural and aesthetically pleasing. So this is great. SUSY tells you why it's the mass that we have. But what's interesting is SUSY isn't really very symmetric. Because if there was a selectron of the same mass as the electron, which is what the theory would say naively, we would have seen it by now. It would have the same charge. Again, it'd be streaming through here. It'd be very easy to identify those. So the point is they've all got very high masses. They must have much higher masses than the normal particles. So the symmetry is broken. It's another broken symmetry like the Higgs. Right? It has fallen into a particular state where they have a very different mass from these. Now, that's a problem for this Higgs cancellation, because if the masses get too far apart, those loops won't cancel anymore. Right? They gradually become, one gets bigger and the other gets smaller as the masses diverge. And to get it to work, they have to be of order of TeV apart at most. Ideally, they'd be the same, but they can't be more than the TeV, otherwise the whole explanation of why the Higgs mass is like it is falls apart. And that's one of the big selling points of SUSY. But of course, the TeV is exactly the LHC regime. So we went into this saying, if SUSY exists, we really, really should be able to see it at around a TeV, because otherwise we can't explain what the Higgs mass is. Okay? So that's really the driver for this. So how do you see this? This is an example. There's many, many other ones. The protons collide on the left. They form a stop, so a SUSY top at the top, and it's antiparticle. That conserves the charge because you pair produce them, one with a plus charge, one with a minus charge. They decay to a normal top and an antitop and produce the lightest SUSY particles, which are here. Now, those can't decay. They can't interact because they don't have any strong or weak or electromagnetic force. And so those will just shoot out from the detector. The point is that they mean that we don't apparently see energy and momentum conservation. So you get an event like this where all the stuff is happening up in the top and there's nothing coming out the bottom. So if we add up all the energy and momentum that we see, we can figure out where these particles must have gone by the fact that there's momentum missing. This is the signature. This rarely happens in the standard model, particularly at the sort of energies that these lighter supersymmetric particles would be coming off. So therefore, if we study missing energy, we can tell that supersymmetric events have happened because they've got large missing energy, and that is very rare. Now, unfortunately, again, we haven't seen that many events with large missing energy. So if we look at this particular case, this case of the tops, the stops, the top that has them in decay mode, you've got to go into all sorts of different analyses. There's 1, 2, 3, 4, 5, 6, 7, 8 different ways of doing it there. All the lines are there. The patch in the middle is where this is saying they've got to be outside those lines, not inside. Okay? So we've excluded that whole parameter space for the two masses. So what this says is the stop mass has got to be heavier than around 900, or the LSP, the lightest one, has got to be heavier than about 400. We can't quite get to this TeV limit yet, but we're getting there. More data will allow us to keep going. Okay, so at some point, we should either see supersymmetric particles, or we should say it doesn't work to satisfy the Higgs requirement, and therefore it loses a lot of its motivation. So one way or the other, we should sort this out over the next few years. Okay, and then this is just one decay. There are many others. I clearly won't go through this plot. Basically, there's 40 or 50 different ways of looking for SUSY, and the green line shows you where you're getting to. So a lot of them are beginning to hit. 1 here means 1 TeV. Have eliminated the possibility of particles being less than 1 TeV. When all that plot is shifted up above 1 TeV, we basically start saying SUSY is looking very ill. Okay? We're not there yet, but we're getting there. So the final thing I'll just talk about is the dark matter, which I mentioned previously. Now, dark matter is weakly interacting particles. They appear to be quite massive. Otherwise, the Planck measurements of the asymmetry of the distribution of the microwave background in the universe would actually look quite different. It would have different clumpiness. So dark matter basically is saying there's a lot of stuff, 25% of the universe is made of dark matter, that we just can't see astronomically. But you can tell it's there because gravities are rotating a lot faster on the outside than they would be otherwise, because there's a lot of mass holding them together that isn't apparently there. The other thing, this fantastic bullet cluster, 2 galaxies had passed through each other, and due to the effects of gravity of the dark matter distorting the stars in the background, you can actually tell where the dark matter is compared to where the matter that you can see is, the gaseous matter, the stuff left over from the collision. And so dark matter really does exist. I don't think anyone debates that anymore. So it's not like SUSY. But the point for particle physics is it's a weakly interactive massive particle, and that is exactly the properties that this LSP has. So if SUSY is true, it would also explain dark matter. And turning that around, when we look for SUSY, we're actually also looking for dark matter. So that's very useful. Dark matter, it can be made in 3 different ways. So you can get it colliding in the galactic core making X-rays. You can get it recoiling off nuclei. There are people in Imperial studying this method. But the one we're most interested in is the formation of pairs of dark matter particles. And in fact, you actually need to produce them with something else. Otherwise, just 2 dark matter particles you wouldn't see at all. So you have to have a gluon coming off as well. OK? So this is us compared to other experiments that are doing direct searches or the annihilation method. The red is us, the green is the other experiments. The 2 are different assumptions on the sort of thing that the dark matter is. The one on the left shows we have not yet got to the stage where we're really competing with the opposition. The one on the right says for those type of models, we're actually doing better than them. So we are contributing to understanding if dark matter exists or not. OK? So gravity. It's one of those interesting things that gravity, if we lived in 2 dimensions, not 3, it would have a different force law. So what that says is, if there are more than 4 dimensions, 3 space and 1 time, gravity would have a different form than it does at the scales that we look at. So if we can probe very deeply into the protons, as I was saying, the wavelength, if you go to higher energies, you get a finer probe, you can see more resolution. Maybe you can see these effects. What it boils down to is, the extra dimensions, you would have excitations in those. So a Z boson would actually have an excited state. And so what we're looking for realistically is heavy Z bosons. And we saw Z bosons go to 2 electrons or 2 muons. Here's another example. So what we'd actually be looking for really is the plot of the Z boson. Here the Z boson is the peak in blue. The blue curve is the sum of all the contributions from the standard model. What we'd be looking for is a peak at very high energies, something that would be caused by extra dimensions. Clearly, there is no sign at all. The data agree with the standard model curve extremely well. So again, there's nothing there. We can set limits on the masses. And in fact, heavy bosons are extremely common in a whole bunch of other theories as well. So this one plot can be used to put limits on lots of other theories. And in a similar way to before, there's a whole bunch of exotics that people are looking at. Some of these are really penetrating into the TV regime. Again, the length of the bar shows you how much has been eliminated, the place where it can't exist. Some of them are still down at the sort of 1 TV level. Lots of different, gravitons, which would be the force equivalents for the gravitational field. Leptoquarks, which is a mixture of leptons and quarks. As you would guess from the name, the heavy bosons I mentioned is the 3rd on the left. But we've still seen nothing there. So we've not seen any known unknowns, we've not seen any unknown unknowns. So at some level, it's getting quite frustrating, but at another level, there's still a long way to go. And so I'll just wrap up by saying, what is the future? I'm not going to try and predict what particles we're going to see, I'll just tell you what's going to happen. The LHC will run as it is now until 2022. We will get 5 times the current data set. Right? That's a lot of more extra data. That's more than the difference between the 750 bumps, right, where we got rid of it. So, yeah, that will allow us to see a lot more detail of what's been going on in these plots and try and push the limits harder or possibly see something. OK? At 2022, there'll then be a 4-year shutdown. So this will be a major upgrade to the accelerator. And that will allow them not to go to a higher energy, but now to go to a higher rate. And so they'll be able to collide more protons together than they are at the moment. There will also be a major upgrade to the detectors. The detectors aren't built to handle this rate. This was an idea since the detectors were created. So basically, we've got to increase the ability of the detectors to read out even more data flow. And then we'll start running again in 2026 and continue for about another 10 more years, which means basically this is the only experiment I will do until my retirement, in all likelihood now, which is a scary thought. But at the end of that, the increase will go up by a factor of 5 or something. We will have 50 times the current data set. So one way of thinking of that is we only have 2% of the data. Now, we've seen the Higgs. That was easy. That was low mass. But now we've got all this stuff at high mass that we're trying to see. And so, in 2% of the data, we made one discovery. maybe there'll be plenty more. Okay? It's still a long way to go. This is a long-term program, and we still have a huge amount of data to come. So just to summarize, I think I'm running a bit late, so I'll just go through these very quickly. Towering intellectual achievement of the Standard Model tells us about the Big Bang. We've discovered the final piece of the Standard Model, and we're trying to check it in great detail to see if it's really the Standard Model. And now we're trying to explore the new regime, the TV area, where there could be all sorts of particles. There are theoretical reasons for believing they exist. Now we're going to run for around 20 more years, and we're going to get a huge amount more data. So there are plenty of opportunities to see. So that's it from me.